Hi everyone, this is NLP Corgi. Today's deep dive is about the paper from Xiamen University titled How Well Do Large Reasoning Models Translate? A comprehensive evaluation for multi-domain machine translation. Most people now know that large language models can translate pretty well in everyday settings. But real translation work is rarely just news headlines or casual chat. It spans medicine, law, IT, literature, and more, each with its own jargon and style. At the same time, a new family of models has appeared, large reasoning models, or LRMs, which are trained to think in structured, multi-step ways. They shine on math and coding tasks, but we don't yet know if that kind of reasoning actually helps with complex, domain-sensitive translation. This paper tackles that question head-on. The study is driven by a few concrete questions. First, when we look across many domains, do reasoning-focused models actually beat traditional language models at translation? Second, is their advantage consistent across language pairs like English-German and English-Chinese, or does it depend on the pair? Third, are LRMs especially helpful when the text is long, structurally complex, or conceptually difficult? And finally, can we boost their performance further just by designing smarter, domain-aware prompts? Multi-domain translation is challenging for several reasons. First, the same word can mean very different things in different domains, so the model has to infer the right domain from context. Second, fields like law, medicine, and IT demand precise terminology and rigid formatting. Small deviations can be serious errors. Third, many texts are long and require the model to maintain coherence and consistency across sentences and even pages. And finally, domains like literature and culture-sensitive content require not just correct meaning, but also faithful style and tone. Traditional language models are typically trained with supervised fine-tuning on large parallel corpora. They're excellent at pattern matching and imitating reference translations. Large reasoning models, in contrast, are optimized with reinforcement learning to produce structured chains of thought. They plan, verify intermediate steps, and refine their own outputs. The hypothesis here is that this extra reasoning machinery might be especially useful for translations that are semantically dense, structurally complex, or heavily context-dependent. The authors compared two families of models. On the traditional side, they evaluate GPT-4o, DeepSeek V3, and Gemini 2.0 Flash. On the reasoning side, they test OpenAI's O1 and O3 Mini, DeepSeek R1, and Gemini 2.0 Flash Thinking. All of these are accessed through their official APIs, and they're run through the same translation and evaluation pipeline so that differences in performance can be attributed to the models themselves, not to tooling. To really stress test these models, the authors assemble a broad benchmark. They evaluate 4 translation directions: English to and from German, and English to and from Chinese. Across these, they cover more than 15 domains. The data comes from well-known benchmarks like WMT, the multi-domain dataset, Corpus, CommonMT, CAMT, and the WMT Literary Translation Task. This gives a mix of general content like news and conversation, technical and biomedical text, culturally loaded material, and even literary prose. The domains are chosen to span a wide spectrum of difficulty. High resource areas like news and social media test general translation ability. Terminology-heavy domains such as law, medicine, IT, biomedical text, and e-commerce stress precise term usage and structure. Low resource or special domains like Quranic text, culture, and common-sense reasoning probe robustness when data is scarce or context is subtle. And stylistically demanding content, including literature and subtitles, tests whether models can preserve voice, rhythm, and tone. The evaluation uses a mix of automatic metrics. Blue measures how much the model's output overlaps with the reference at the word and phrase level. Comet is a reference-based neural metric that focuses more on semantic similarity and correlates better with human judgments. Comet Kiwi is reference-free, so it can still assess quality even when the reference is imperfect. On top of these, the authors use an enhanced M2M framework powered by an LLM to annotate detailed error types like mistranslations, style issues, and terminology mistakes. To dig deeper than a single score, the authors extend the M2M framework with an error taxonomy tailored to LLM outputs. They track 7 high-level dimensions, including accuracy, fluency, style, and terminology, plus categories for source errors and non-translation. Under these, they define 25 specific error types, such as hallucination, semantic repetition, and cross-domain confusion. DeepSeek V3 is used as a consistent automatic annotator, guided by a strict prompt to identify up to 5 major errors per sentence and assign severity levels. For English-German translation in both directions, a clear pattern emerges. In open, flexible domains like conversation, news, social media, and e-commerce, reasoning models tend to score higher on semantic metrics like Comet and Comet Kiwi. Traditional LLMs, however, usually win on blue, especially in rigid, terminology-heavy domains such as law, medicine, IT, and Quranic text. The authors argue this reflects training differences. Traditional models, often fine-tuned on parallel data, imitate reference wording more closely, while LRMs, optimized with reinforcement learning, prioritize global semantic plausibility, even if the wording diverges from the reference. For English-Chinese translation, the story is similar. LRMs again do well on semantic metrics in flexible, user-focused domains like e-commerce and conversation, but they lag in law and science, where precise terminology and structure are critical. Interestingly, Chinese-centric models like DeepSeek v3 perform particularly well on culture-sensitive datasets, suggesting that pre-training data alignment with the source language and culture can be as important as the reasoning paradigm. Overall, translation quality here is shaped by both how the model reasons and what it has seen during training. A key takeaway is that different metrics tell different stories. Traditional LLMs often achieve higher blue because they stick closer to the reference wording, which blue rewards. LRMs, by contrast, tend to score better on Comet and Comet Kiwi, indicating stronger semantic alignment and human-like phrasing. This means that a lower blue score for an LRM in a terminology-rich domain doesn't necessarily imply a bad translation. It might simply be using valid paraphrases or alternative terms. That's why the authors emphasize multidimensional evaluation rather than relying on a single metric. The MQM analysis adds nuance. On average, traditional LLMs achieve lower overall MQM scores, meaning fewer weighted errors. However, LRMs actually do better in the Quran domain, where their explicit reasoning may help with ambiguous or atypical language. When the authors break down error types, LRMs tend to have slightly fewer accuracy and fluency errors, and fewer cases where the translation is completely off. Their weaknesses show up in style and terminology. They're more likely to drift in tone or pick inconsistent or non-standard terms. Looking at the error category percentages, the differences are subtle but telling. LRMs are at least as good as traditional models on accuracy and fluency, and they rarely produce completely unrelated text. Where they stumble is in style and terminology. They may choose a correct but stylistically off phrase, or they may fail to maintain consistent term usage across a document. This pattern suggests that LRMs are very good at modeling meaning and sentence structure, but they still need better mechanisms to respect domain-specific style guides and terminology constraints. To zoom in on terminology, the authors use the WMT23 terminology shared task, where specific source-target term pairs must appear correctly in the translation. For Chinese to English, LRMs slightly edge out traditional models, with DeepSeek R1 achieving the highest accuracy. The authors attribute this to LRM's stronger reasoning and contextual understanding, which help resolve ambiguous Chinese terms into natural English equivalents. For German to English, however, traditional LLMs do better. Because German and English are lexically similar, simple pattern matching and reference imitation are often enough, favoring the traditional training paradigm. These terminology results suggest a practical guideline. For language pairs that are structurally and lexically distant, like Chinese to English, LRM's reasoning capabilities can be a real asset in disambiguating terms and choosing natural translations. For closer pairs like German to English, traditional LLMs that imitate reference patterns may be more reliable for strict term matching. The authors argue that to fully unlock LRMs in terminology-heavy settings, we'll need ways to inject explicit term constraints into their reasoning process, so that they can plan around required terminology rather than just hoping to pick it up implicitly. The authors also compare performance when models translate isolated sentences versus full documents. Across 5 domains, LRMs consistently achieve higher Comet and Comet Kiwi scores at the document level. This suggests they're better at capturing long-range dependencies and maintaining coherent discourse over multiple sentences. The advantage is especially clear in conversation and news, where meaning often depends on earlier context. Reasoning mechanisms like long chains of thought seem to help LRMs plan and maintain consistency across an entire document, not just within a single sentence. To understand how prompting interacts with reasoning, the authors test 3 prompt styles using DeepSeek R1. The first is a plain instruction to translate, with no domain information. The second explicitly tells the model the domain, like law or medicine, and asks for that style. The third asks the model to infer the domain from the text and maintain the source's domain style in the translation. They evaluate these prompts across IT, law, and medical domains using BLEU, COMET, and COMET Kiwi. The results are striking. The domain inference prompt P3 consistently delivers the best semantic scores across IT, law, and medical. Explicit domain labels P2 often give the highest BLEU in law, likely because they push the model toward formulaic legal phrasing that matches the reference. But P2 usually trails P3 on COMET and COMET Kiwi. Both domain-aware prompts outperform the plain prompt on semantic metrics. This suggests that LRMs benefit most when they are encouraged to reason about the domain from context, rather than being handed a static label. To probe how models handle varying difficulty, the authors ask DeepSeek V3 to rate source sentences from 1 to 5 based on structural complexity, vocabulary, grammar differences, and contextual demands. On the easiest sentences, traditional LLMs perform very well, with high BLEU and COMET. But as difficulty rises, LRMs start to pull ahead, especially on semantic metrics. Models like OpenAI O1 and Gemini Flash Thinking maintain stronger COMET and COMET Kiwi scores at the highest difficulty levels, indicating better robustness when the translation problem is genuinely hard. A concrete example comes from a Chinese common sense dataset. The source sentence uses an idiom that literally means to go into the sea, but figuratively refers to leaving a stable job to start a business in the 1990s. DeepSeek R1's reasoning trace shows it unpacking this idiom, considering options like went into business, and then settling on ventured into business, which matches the reference and captures the sense of risk. This illustrates how explicit reasoning can help resolve lexical ambiguity and choose a more nuanced, context-appropriate translation. The authors also look at how many tokens each model uses on a multi-domain English to Chinese test set. LRMs often produce significantly longer outputs than traditional LLMs. While they maintain strong COMET Kiwi scores, they don't always improve BLEU or COMET in proportion to the extra text. This supports the idea that LRMs can sometimes overthink, applying heavy reasoning even when the input is simple. A promising direction is to make reasoning depth adaptive, so models can respond concisely to easy cases and reserve deep chains of thought for genuinely complex translations. Putting everything together, the study finds that large reasoning models are particularly strong when translations are semantically complex, long, or otherwise difficult. They shine on document-level tasks and on meaning-oriented metrics like COMET and COMET Kiwi. Traditional LLMs, however, still have an edge in terminology-intensive and stylistically rigid domains, where strict adherence to reference phrasing and formatting matters. Domain-adaptive prompting, especially prompts that encourage domain inference, can substantially improve LRMs. And the best choice of model family depends not just on the domain, but also on the language pair. The authors are careful to note several limitations. First, all experiments are on high-resource pairs, English-German and English-Chinese. The conclusions may not hold for low-resource or typologically distant languages. Second, the MQM annotations are produced by a single model, DeepSeek V3. This ensures consistency, but it also risks importing that model's own biases into the evaluation. Future work will need more diverse language pairs and more robust human or multi-model evaluation setups. Looking ahead, the paper suggests several directions. One is to more tightly integrate structured reasoning with explicit domain and terminology constraints, so LRMs can think deeply while still obeying strict domain rules. Another is to design systems that adapt prompts and even choose between models based on domain and difficulty. Extending this kind of evaluation to low-resource and typologically diverse languages will be crucial. Finally, evaluation itself should blend human judgments, reference-based metrics, and reference-free signals to capture the full picture of translation quality in real-world, multi-domain settings.